So our second speaker is Dr. Hélène Ruffieux. Hélène is a research fellow funded by the Lopez Loretta Foundation and joined the unit in August 2019. She's also the recipient of the 2021 Young Biometrician Award. She leads research on Bayesian modeling for high-dimensional data, which involves designing scalable hierarchical approaches for sparse regression, latent factors, and graphical modeling. This research is applied to biomedical studies with diverse clinical and biological data, including genome-wide association studies and molecular quantitative trait locus studies. In order to help advance our understanding of the molecular processes driving disease risk and progression. Her talk today is entitled A Functional Principal Component Analysis Framework to Characterize Systemic Recovery from SARS-CoV-2 Infection. Over to you, Hélène.
Thank you, Brian. Thank you, Brian. And I also would like to thank the rest of the organizing committee. I really appreciate the opportunity to present today, and I look forward to the rest of the day. The central theme of this talk is going to be functional principal component analysis, or FPCA, which is a tool that's becoming more and more relevant for biomedical research since longitudinal data sets really multiply now. But before I tell you more, I'd like to say that I'm going to present two items. And these items are the results of joint work with several colleagues, but in particular two colleagues whose contribution was really essential here. So Christoph Hess, who is a professor of experimental medicine, and with Christoph, we used an FPCA framework to model recovery trajectories of immune parameters in COVID patients from Cambridge hospitals. And then Thuy Nolan. So Thuy is a research associate here at the BSU. He's also an expert in Bayesian FPCA modeling. And so with Thuy, we are working on a variational multivariate FPCA approach. He actually is the primary contributor to this work. So most of this talk will be on applied results. And I will actually start with the applied work, which is probably a bit unusual, but I think it also nicely reflects the way we did this research, because it's really specific questions we had in the COVID study that motivated the development of the multivariate FPCA approach. And I think more generally, I think it nicely reflects, kind of a trademark of the BSU, because most of the methodology we develop at the unit is actually triggered by practical needs to address applied questions. Okay, so as we all know, since the beginning of the pandemic, there has been a lot of research on the immune response to COVID-19, and in particular on what may drive severe infections. But now that the risk of hospitalizations has dropped, the focus of the research is kind of slowly shifting towards questions around incomplete recovery and non-COVID. So long COVID is really becoming a public health issue now, because we know that even individuals with mild infection can develop symptoms that will last for months, right? And so with this study, really, we wanted to see if we could clarify the biology behind incomplete recovery at an organismal level, so at a systemic level. And also we wanted to see if we could come up with a basis for predicting the risk of incomplete recovery. Right, so this is the idea. Of course, it's not an easy task for multiple reasons, and I'm listing two reasons here. So first, COVID can affect several organs, and it can perturb a very broad range of biological parameters for months, right? And so if we want to study these perturbations at an organismal level, we need very detailed data that quantify parameters across several systems. So across the immune system, across the metabolic system, across the inflammatory system, and also ideally we need longitudinal versions of this data if we want to understand recovery, right? So we need samples that are taken regularly over months after disease onset. And so clearly it's not easy to gather such a wide spectrum of data for the same patients, and it will take months by definition, simply, right? So this is the first point. And the second point is that symptoms can be very different from one individual to another. So some people may experience fatigue, some other people may have difficulty to breathe, etc. And actually I read that more than 50 different long COVID symptoms have now been referenced by different reviews, right? So it's huge. And now these symptoms may also have very different causes. So in some cases, they may be kind of direct sequelae of some damage that was caused during the acute phase of the disease. But other symptoms may be linked to some chronic states, which involves biological processes that are actually very different from those of the acute phase. And so really we have this clinical heterogeneity that translates at a molecular level. And so if we want to understand this better, we really need some statistical methodology that's able to disentangle this patient heterogeneity over time. And we also need to understand the interplay between the clinical disease course and the different biological trajectories over time. So this is the idea. So as you understood already, we will try and tackle these questions using functional principal component analysis mainly, assuming that we have the data. So this is a problem. And okay, so we actually do have some data. So what do we have? Well, we have samples from patients that were recruited across a range of clinical severity classes, depending on their hospitalization status and oxygen needs. So from A, asymptomatic, to E, hospitalized and ventilated patients. So this is the worst class. And we also have 45 COVID negative healthy controls. And so the data were longitudinal measurements that were covering actually 1 full year after disease onset. And they covered different types of data, so immune cell subsets, polar metabolites, glycogen lipoproteins, inflammatory markers like CRP and cytokines, and also other clinical information like questionnaires on long COVID symptoms. Okay, so for time reasons, I will really focus on the FPCA analysis in this talk, and I will only very briefly introduce the other kind of satellite analysis that we did by walking you through the graphical abstract of our manuscript here. So, of course, I don't expect you to be able to read the details in this snippet here. I just use them to give you a high-level overview or a flavor of these additional analysis and findings, actually. So what we first tried to do was to simply explore the data with some very standard differential abundance and association analysis. So we use linear mixed models to try to identify the main markers of COVID-19 and try to see how these findings related to published findings on other cohorts, right? And so what we found was mostly in line with existing knowledge. So we found important disruptions across many parameters of the inflammatory, metabolic, and immune systems. And we also found that these parameters largely covaried with CRP. So CRP, I'm sure you know, is a marker of inflammation that's almost systematically measured in blood tests. And so from this, we could conclude that first, our cohort seemed to be a representative SARS-CoV-2 cohort. So that was sort of a good sanity check to have. And the second thing is that we noticed that these analyses are actually way too coarse if we want to address questions around systemic recovery, because they tell us very little about the patient-to-patient variability in these disruptions, right? And also the longitudinal measurements are not really exploited here, right? And so with this, we had a clear motivation to introduce the FPCA analysis, and this is also what I'm going to do now. Okay, so the main objective of FPCA is to reduce the dimensionality of functional data in some useful way, right? And in some useful way, which actually accounts for the major sources of variation in the data. So in the COVID study, we want to use FPCA to characterize the variations in the patient parameter trajectories in a way that we hope will help us explain the dynamics of recovery and the interpatient heterogeneity in this recovery. So here we assume that we have n realizations of a smooth Brunner function, y of t, and we also assume that there exists a continuous mean function and a continuous covariance function. And so FPCA is actually based on the following decomposition of the covariance operator, where here we wrote the eigenvalues in decreasing order. I'm sorry, I can't use the mouse, so I'm obliged to show on the screen. I hope you can see something online or have an idea of what I'm showing. But now, actually, FPCA uses the so-called Karinin-Loew theorem, which states that each curve can be expanded into a sum of the mean function, mu, plus a series of random deviations from the mean, where each term in this series is actually a score, zeta IL, multiplied by the eigenfunction of the covariance operator psi L. And what we have in addition is that these eigenfunctions are orthonormal, and the scores are centered, they are uncorrelated, and they have a variance lambda L. Right now, of course, in practice, we truncate the series at some positive integer capital L here, and we typically choose capital L by looking at the proportion of variance explained by the first few eigenfunctions. So typically, the first 2 or 3 eigenfunctions will capture most of the variability in the data. And then, of course, we don't observe the continuous curves themselves, but we have a discrete set of observations which have measurement error with residual variance sigma epsilon squared here. Okay, so let's see what this gives us on the longitudinal CRP data. So here we really first wanted to see what drives the variation in inflammation trajectories of symptomatic patients. And so here I'm showing the first 2 eigenfunctions over the first 7 weeks after symptom onset. And so you see that together they essentially explain all of the variability in the data. And here you have a scatter plot with the corresponding scores. And so we have 1 point per patient here, and the x-axis shows the scores corresponding to the first eigenfunction, the y-axis shows the scores corresponding to the second eigenfunction. Now, it turns out that these first 2 eigenfunctions have very nice interpretations in the sense that they reflect important aspects of inflammation trajectories. Right? So, in fact, the first eigenfunction is a proxy for the severity of inflammation. So it's the solid line here, and you see it's above 0 over the whole time window here, which means that a patient with a positive score for this first eigenfunction will have higher than average CRP level over their disease course. This is because, remember, the score multiplies the eigenfunction here, and so we'll have a positive deviation from the mean here. And actually, if we look at sort of the gradient of gray here for these points along the x-axis here, and also at these box plots for this first set of score, we see that they actually reflect the clinical severity classes B to E quite well here, which was interesting to see and also kind of comforting in terms of the interpretation we had of this first eigenfunction. Now we can look at the FPCA trajectories that are estimated for 2 examples of patients with extreme scores. So here you see this patient here with a large positive score on the x-axis who has high inflammation levels over the whole disease course, while this patient here with a large negative score has essentially normal levels. And here I should say that the horizontal gray band here, I don't know if you see it, but there is an horizontal gray band. This is the interquartile range of CRP levels in healthy control. So it essentially represents normal inflammation levels. Okay, now if we look at the second eigenfunction, it's actually a proxy for recovery from inflammation. And again, if we take an example of patient with a positive score, it means that we will typically see, their CRP level drop over time. So again, 2 examples here. a patient with a large positive score on the y-axis whose inflammation resolves well, and a patient with a large negative score on the x-axis whose inflammation gets worse, essentially. So really this course reflects the extent to which each patient will recover from inflammation and kind of the dynamics of this recovery. So just a quick note here to say that we've obtained these results with a version of FPC approach that TUI has developed, and I will read the full reference at the end. But at the time we did the COVID study, we actually relied on a published frequentist approach by Luo Xiao and colleagues. So you may notice that the estimates of the scores are slightly different here and here, but the interpretation was the same. Okay, so where did we go from there? Well, I said before that FPCA is a powerful dimension reduction tool, and in particular, the severity and recovery scores are a very nice summary of the CRP curves that we can then use for further analysis tasks, right? So here in particular, what we did is that we fitted a Gaussian mixture model to this course, right? And so we uncovered 3 clusters of patients with distinct inflammation recovery profiles, as you can see from this longitudinal mixed model with these splines. And this really aligned with the interpretation we had on the scores as expected. So for the gray group here, with rather low severity scores, we see that it has essentially no inflammation. For the blue group with rather high recovery scores, we see that inflammation starts high but then resolves well over time. And for the red group with the most unfavorable scores in the end, we see that inflammation tends to persist over the 7 weeks post-symptom onset. Okay, so then we asked, okay, but can we explore the hypothesis that inflammation may be a central mediator of organismal recovery? And this is a very plausible hypothesis that has been explored by different studies. It's sensible that inflammation will play a central role here. So how did we explore this? Well, we tried to characterize these groups not only in terms of the dynamics of inflammation, which is kind of done here almost by construction, but also in terms of their risk of death, in terms of their immune and metabolic profile, so in the short term, but also in the longer term, over 1 full year post-symptom onset. I'm going very fast here, but just to give you an idea. And also we try to distinguish them in terms of the long COVID symptoms. And here in particular, we uncovered a latent factor, which is mostly driven by neurological symptoms. And it turns out that it distinguished the 3 groups quite well. Although there is quite a lot of variability here, which may have different explanations, and in particular may be linked to the fact that symptoms are subjectively perceived and self-reported. So that's one explanation. There are certainly others. And what we also noticed is that this kind of neurological signature here may actually be linked to a persistent disruption of the kynurenine metabolic pathway, which is a long-term disruption that we've observed in our other types of analysis. Okay, so then we asked, okay, but can we leverage this and maybe build a predictive model on biological parameters that were collected very soon, or from samples that were collected very soon after symptom onset, to see if we could obtain an early signature of incomplete recovery. That would be very useful in terms of therapeutic recommendations, right? Ideally and ultimately. And we found a signature, and what was interesting here is that the metabolites from the kynurenine pathway again appeared with a strong weight in this signature, along with other parameters from other types of data, because this is a composite signature. But in particular, we found parameters which are involved in immune pathways, which we think may be acting in concert with kynurenine metabolism. So that was interesting to see. Okay, so far with this analysis, we really focused on characterizing clusters of patients that were obtained from a Gaussian mixture model of the CRP FPC scores. And so this involved, doing some kind of sensitivity analysis to assess the stability of these clusters, And here we could use the cluster assignment probabilities to try to evaluate the extent to which some patients at the cluster boundary here were weakly assigned, and make sure that our results were actually robust to these patients changing clusters. But I think a very appealing feature of FPCA, which we must keep in mind, is that it also provides patient-level estimates, so patient-specific scores and patient trajectories estimates. And so this would allow us to avoid such kind of cluster-based considerations, at least in some cases. And so what we did is that we analyzed not only CRP by FPCA, but all other data types by FPCA. And here I'm showing, again, an example of 4 important metabolites of the kynurenine pathway, which I mentioned before. And here we see 2 things. So the first thing is that we have a single set of scores that are estimated from all 4 longitudinal variables here. And this is because we are using a multivariate version of FPCA. Right? And I will show you a model in a minute. But the idea is that we really capture, with these scores, we capture the temporal covariations of these metabolites within the kynurenine pathway. And the second thing is that the first 2 eigenfunctions, again, had the same nice interpretation as before, in the sense that the first eigenfunction is again a proxy for the severity of the disruptions. In fact, we know that patients with severe infections will tend to have high levels of the first 3 metabolites and low levels of tryptophan. And the second eigenfunction again reflects parameter recovery over time. And now it turns out that these interpretations hold for all other data types that we analyzed by FPCA, and the scores for these different FPCA analyses were highly correlated. So these are the severity scores, and by the way, you again see this gradient of gray here, which means that they again reflect the clinical severity classes quite well here. These are the recovery scores, so the correlation is a bit weaker here, but still we can notice it. I think it's more interesting to actually look at the conditional independence and conditional independence graphs for the severity and recovery scores. And what they suggested here is that CRP may indeed be a central mediator of these severity profiles, or at least its scores are directly associated with the scores from all other data types, or almost all other data types. And if we look at the network of recovery scores, it suggests that recovery profiles are kind of mediated by interplays between inflammatory cytokines and metabolites from the kynurenine pathway, but also between inflammation and lymphopenia. So lymphopenia is when you have low levels of lymphocytes. And this was also very plausible from a biological perspective. So I'll try to finish to be a bit quick. Yeah, with this example, really, we have, you know, a clear motivation of why multivariate FPCA is interesting and can really capture the temporal covariations of related parameters. And this really helped us to clarify how the immune, metabolic, and inflammatory systems kind of coordinate the organismal response to infection and organismal recovery over time. Okay, so the results I showed you here were again obtained with a frequentist multivariate FPCA approach. And this is where with TUI, we thought it would be good to propose something for Bayesian multivariate FPCA, right? And this is a very small part, so I will finish quickly. Why is this interesting to look at Bayesian multivariate FPCA? Well, in frequentist FPCA, we need to estimate the covariance function, and this requires a series of smoothing and eigendecomposition steps, which can be costly computationally, and also they involve a number of choices to be made. Now, in the Bayesian case, we don't need to estimate the covariance function because, in fact, we treat all parameters as unknown, and we estimate them jointly, directly from the Karnaugh-Lorentz expansion. So I said before that TUI has already proposed a univariate Bayesian FPCA approach based on variational message passing inference. So I won't say more about variational message passing. I won't have time. And also, it's not my area of expertise, but I strongly recommend reading TUI's paper or you can actually directly talk to him later if you're here in person. And so we have now developed a multivariate version for this work, right? So let me show you the model. So first, actually, in the univariate case, so we use non-parametric regression to model the mean function and the eigenfunctions. So we have a T by K design matrix C of T, which is constructed from a set of K spline functions. And nu mu and nu psi L are the vectors of spline coefficients. So this is the model. So we use a Gaussian likelihood specifications over the vectors of observations. We use Gaussian priors over the vectors of scores and of spline coefficients. And we use half-Cauchy priors on these variance parameters. Now, I said before that an appealing feature of FPCA is that it provides orthonormal eigenfunctions and uncorrelated scores, but you notice here that we haven't enforced these restrictions within the Bayesian model itself. Right? So it means that the algorithm is simply going to pick any set of curves that fit the data. But luckily we can regain this orthonormalization by post-processing the posterior estimates. So that's sort of very convenient and a good route. Now we can flexibly extend this hierarchical model to P longitudinal variables indexed by J. And again, an important point here, which I already emphasized in the Carnunian pathway illustration, is that the scores are now common to all P variables. And so this means that we have a very parsimonious representation of the data in terms of the main modes of joint variations across these P variables. And again, it can be shown that there exists a unique set of orthonormal eigenfunctions and uncorrelated scores, such that we can actually regain the FPCA decomposition corresponding to a multivariate version of the Carnunian law F theorem for this new Hilbert space here. Okay, so do I have 1 more minute or yeah? Okay, so very quickly, so how does this perform in practice? So here we simulated 100 curves for 3 variables using these mean functions and orthonormal eigenfunctions, and we use Gaussian scores. And these are the fits that we obtain with our variational inference approach in blue. And we also added a comparison with MCMC inference in gray, which is much slower, but we use it as a gold standard and as a sanity check of the quality of our variational approximation. Actually, you may not notice the 2 colors here because the agreement is actually quite good here. These are the estimated scores after orthonormalization, and the ellipses are the 95 credible boundaries for this course. So you see we get very good inference on this course in general. Actually, there is a slight underestimation of the variance with the variational contours in blue compared to the MCMC contours that you may notice, but it's very minor, I think. And finally, these are the eigenfunctions with the true curves in black and the fits from 50 different replications in blue here. Okay, so let me conclude very quickly. So I hope I have convinced you that FPCA and multivariate FPCA is a powerful tool to characterize the variation in longitudinal biomedical data. And with the patient level FPCA estimate for the COVID disease trajectories and scores, we could really come up with some mechanistic hypotheses. And also we could make a case that it could be beneficial to include specific markers in routine blood tests because they may be good early predictors of incomplete recovery. Now, of course, will be very important to try and validate all these findings in other cohorts, and this is something we are looking at the moment. Okay, so I'd like to thank all my collaborators, and in particular Thuy Nolan, Christophe Hess, and also Sylvia Richardson. And so with Thuy, we would like to upload a preprint for our multivariate FPC work pretty soon, so will happen soon. And you can already access our preprint on the COVID study. hopefully the latest version of this work will be published soon. And we also have two Shiny apps with the FPCA trajectories and scores for each patient and each data types, and with the pilot predictive model of incomplete recovery. And thank you very much for your attention.
Thank you very much. Thank you very much, Hélène. Questions? Shall we start with anybody online first? If you have any questions online, please raise your hand. We'll come to the audience just now. Thanks. No? Okay, we can go to the in-person audience. Sumitra?
Hi, great talk, Hélène. Yeah, it's quite interesting work. I'm a bit confused about your choice of eigen decomposition of the covariance function. I mean, like, if you read any kernel methods textbook, they will suggest exactly doing opposite to what you are doing. So you are not utilizing the kernel trick. The whole point of the reason why kernel methods were invented is that you do not have to deal in the eigenspace. You can actually use those inner products and then compile your nonlinearities in the reproducing kernel Hilbert space. So for example, if you look into your eigenoperator equation where you're solving the integral equation. No, if you go back to the earlier one. Yeah, so if you take that I to infinity, you end up with a Gaussian process, right? That's a kernel machine. So what I didn't understand is that the only benefit I would have to do this eigen decomposition not using the non-parametric features that you get with any kernel machine is computational reasons. But since Gaussian processes these days, there are many well-known computationally efficient techniques to do inference. I don't understand why you are throwing away the non-parametric benefits here.
Okay, so I think we should discuss, because first of all, I'm not really aware of the literature you're referring to now. I'm not exactly sure what you mean here, but to me there are two ways of going about this FPCA approach. The first thing is that you can work directly with the covariance function and smooth it, and then obtain the eigen functions and scores, and that's what's done in the frequentist setting in particular. There may be Bayesian approaches that do this as well, but Bayesian approaches tend to work directly with this decomposition here. But that wasn't exactly your point, right?
No, my point is that if you look at that equation of the covariance operator, that's the integral equation. Yes. And if you want to solve it analytically, that's only possible when your covariance function has a power spectral density that is rational. And that's very few handful of covariance functions. But otherwise you have to do it numerically. Okay. So rather than doing that, if you just take your I to infinity, that gives you a Gaussian process. Okay. So the point is, why don't you use a Gaussian process?
Well, because I'm not even bothering with this covariance operator. Actually, I'm working directly with the Carino law of expansion. Oh. So I'm estimating the parameters directly from there, and then transforming the procedure estimates to obtain the orthogonalization and okay. So okay. That's why, I guess.
Okay, thanks.
I suppose the eigenfunctions do give you a lot of information overall in terms of what understanding the disease.
Yeah, that's also true.
Oh, you can throw it over there.
Thank you. Thank you for the talk. So, so you have
multiple different sets of variables. So I'm wondering, do you think if we analyze each set of variables separately and then somehow combine them, would that help for the interpretation or improve the performance?
So you mean several types
Yes.
of variables here? So I think it's a great question. I think we could do several things here. So what we did is that we treated each, so first of all, each data types involve a certain number of variables, right? So it can be several dozens of variables. What we did is to treat these different data types separately and analyze each of these data types by FPCA separately, and then looked at the scores, how the scores correlate, because we wanted to understand how each of these systems reflect give us some information about the severity and the recovery profiles on their own, right? Yeah. And then use the scores to try to compare these type of information. Because, for instance, if you take the cytokines, they have a very short half-life. So they may go back to normal level very quickly after the infection. It's not the case of lymphocyte, for instance, right? So, and so analyzing them separately would allow us to understand this a bit better, right? But it's also valid that since they contain and they encompass like similar information about recovery, and it makes sense to analyze them jointly. And this we did, for instance, with our predictive modeling, where we really try to come up with a composite signature. And there we can start to understand how these different data types coordinate, right? And in response to infection. And yeah, so both approaches are useful and helpful, I think.
Okay, thank you very much.
Thanks. I was wondering how much the sampling structure, which I assume you don't have much control over, affects the inference, because presumably you can imagine that you might like to sample more densely in regions of time where the biological variation is kind of faster or more significant. Mm-hmm. And if the biological variation kind of smooths out at the end, you might not want to sample a lot at the end of the process.
Yeah, so it was the case actually. So patients were sampled more regularly at the beginning, just after infection, and less regularly at the end. So it's a very valid question, and it's true that we could try to think about this more and see how this affects the results. I must say that the FPCA analysis focused on the first 7 weeks post-symptom onset, so it was rather, a regular sampling during these first 7 weeks. It's only then, after 6 months or so, that it became less regular. And the reason why we focused on the first 7 weeks was that we really wanted to understand how acute inflammation and inflammation during the convalescence phase could relate to long-term symptoms. So we really wanted to focus on this time window, which was also convenient from the perspective of your question, I guess. Yeah.
One final question, if it's a quick one.
Sorry, just one quick follow-up then. So you were saying that I noticed during the talk, your sample size went down to 113 symptomatic people. And when you were just answering that question, you were discussing, so is your analysis only of symptomatic?
Yeah.
So asymptomatic was not in there?
Yeah, that's a very good question. And there are two explanations for this. So it's a choice first. Mm-hmm. And the reason we chose not to include asymptomatic patients was because there was a difference in the temporal alignment of their trajectories, in the sense that for symptomatic patients, time was measured since the day of their symptom onset, while asymptomatic people were measured from the date of their first positive swab. since they were asymptomatic. So we thought it may have introduced some bias in our analysis. That's why we excluded them. And the other kind of side reason was more on the interpretation. It sounded a bit, wrong to talk about recovery for those asymptomatic individuals. But it's a side, it's a side reason.
But I mean, if you're going to think about long COVID, then the asymptomatic are also quite important.
Yeah, we didn't have much, data,
Yeah.
honestly, on the questionnaires for the asymptomatic. I think we didn't have any, actually. Yeah. So, but it's a good point.
Can we thank Hélène as well as Thomas again for the interesting talk?